All right, so we're looking at the notes here for Thursday, October the 13th, and we're looking at reaction mechanisms. It's a pretty short section in your notes, and you might remember my talking about this. It was, I believe, in the very, very first day of notes where we looked at some of the homework problems together the next day. And I talked about how a reaction mechanism could have more than one step, and that the slowest step is going to determine what the reaction order is. But we're going to get into that in the notes today. We'll be looking at reaction mechanisms and also at catalysts to the very bottom, and then we'll be done for the day. You guys do have the homework on the calendar today. It's page 670, 671, and then it's numbers 65, 70, 72, and 74 to look at. So here you have that a reaction mechanism is pretty much going to be a sequence of single reaction steps that sum up to your overall reaction. So we're looking at single reactions that add up in a sequence to make one overall big reaction. So let's write that down here. So it's a sequence of single reaction steps, and they sum up to the overall reaction. So here you have an example of A and B. They react together to form a new compound C, and then C that was just produced ends up reacting with one of the reactants from the very first part. So C goes with A to produce D. And once you have the D, now you could actually make your E and F. And if you were to look at the overall reaction here, you would cross out anything that appears on both sides as you're summarizing this out. So the C, there's a C on the left, there's a C on the right. You also could see that there's a D on the left and a D on the right. And if you were to summarize the left and the right side, you would say 2A's plus AB, so 2A's plus B, is equal to a F or E plus F here. And this guy right over here would be the overall reaction of what happened. So C and D, we have a name for them. Notice how they're created during the reaction and then it's used up during the reaction, but it's not one of the final products. And we say that C and D are called reaction intermediates. Okay, so a substance that is formed during a reaction, so we create it during one of the steps, but then they end up getting used up during the reaction itself. If you guys are looking at your activation energy graph over here, and you might remember doing this on the light stick here, and we said that here to here is your activation energy for the reaction to happen. Your intermediates are going to be found right here at the highest point of your potential energy of the reaction. So we say that there is a lot of potential energy for those reaction intermediates, but then they quickly get used up and that goes back down. So for an elementary step, this is another new definition that we have. So it's a single molecular event. Okay. And you can't break it down into any more simpler steps. So it cannot be made up of simpler steps. Okay, so an elementary step, it's characterized by what kind of form it is in. And we say that that's the molecularity here. And you could have a unimolecular elementary step or a bimolecular reaction step. And an example of something that would be unimolecular here is if you just have one single reactant that is going to be decomposed or arranged. So an example that you guys would have here would be like ozone O3. You have just one single molecule, and it is breaking down into oxygen gas plus just a free radical of oxygen right there. Versus a bimolecular is when you have two particles that could actually react. And an example of that is if you had O3 plus O. So you can see you have two different molecules or two particles that are able to react, and then you form something brand new out of it. Another way you could have a bimolecular reaction is if you could have just one type of substance, but if you had two of them like that represented with a coefficient, this also would be considered bimolecular as well. Yeah, so if you were to look back over here, we have this reaction mechanism. It's made up of 1, 2, 3 overall steps, right? So it's a mechanism of reaction 1, reaction 2, reaction 3. These individual steps themselves, they would be called elementary steps. So this is an elementary step, that's an elementary step, and that's an elementary step. So these 3 individual elementary steps make up the mechanism. And you could categorize each of these steps by looking at how many molecules we have in each step. So step 1, there's 2 different particles that are reacting, so it's bimolecular. This is bimolecular as well. And then for reaction 3, you have something that is unimolecular. And you might be thinking, well, what happens if you have 3 different things? A termolecular step. If you looked at the book reading for that part, they mentioned that those do occur, but not with great frequency, which is why it's usually just broken down into 2 different kinds. Okay, so next we're going to look at these different reaction mechanisms, and we're going to talk about how does it affect how fast the rate is going, or the rate law that we came up with before through our last few days of notes. And remember this, I would say this is a very important thing to remember. Your rate law is a reflection of the slowest step in the mechanism. Okay, and the rationale for this is if you guys think about some sort of a factory or an assembly line where you're trying to make one product at the end of the line, and you have several people each doing a very crucial part of the production of the thing itself. If you have one person that is making some sort of a widget and it takes them a really long time to make that one widget, and then they pass that widget down to the next person so they could do something with that widget to make your final product, if there's one step in the production of that product that is very, very slow, it's actually going to slow down the entire thing. So we say whichever elementary step basically is going to be very, very slow in the mechanism, that is what your rate law is made up of. So that's why oftentimes you take a look at the overall equation, and we can't just make a rate law by looking at the coefficients here from the 2a and the b, because we don't know, is it step 1, step 2, or step 3 that limited the rate of the reaction itself. So we would say here, once you determine which step is your slow step, the coefficients, so your coefficients of your reaction, so the coefficients of the reactants in the slowest step, they are going to be the orders for the rate law. So once you know the slow step, that's when the coefficients actually do come into play into coming up with the exponents or the orders for your actual rate law. And this we've talked about as well. But your intermediates, the guys that get created in the reaction but aren't a part of the final product, like earlier we said it was a C and the D, these guys here are not going to be expressed in your actual rate law. So to remove in rate law, all you have to do is you express it in terms of its reactants. And then we're going to substitute. Oh, I don't know why I changed color there, but we'll go with it. Okay, so here's an example here. You have this reaction of nitrogen monoxide reacting with oxygen gas, and we make nitrogen trioxide. And then we have another step in the reaction. And so these are the 2 elementary steps here. we're told that the very first part of the reaction is like the fast step. So this is the step that we're not worried about. It happens very quickly, and they also do mention that it's reversible. And you could see that because we have a double arrow, which we learned about last year in equilibrium. In the second example, or the second elementary step that we have a slow determining, or a slow rate determining step here. Meaning this is the reaction that is going to determine how fast the overall reaction is going to happen. And we know that we're going to be taking this reaction right over here and turning it into our rate law because it's a slow step. But we could see if we took these two equations and then actually tried to come up with a real overall reaction. And I want to get rid of anything that is the same on the left and the right side. So the nitrogen trioxides, I could see that these are both on the left and the right, and those cancel out. So my overall reaction here, if I were to sum this up, I have 2 nitrogen monoxides, so 2NO plus oxygen gas gives me 2NO3 here. So if you look here, this would be your overall reaction of what's going on. You start off with 2 of these guys, 1 of these guys, and you make 2. Oh, I messed that up. It's not NO3 there, but it should be NO2. Okay, and you could see that in my overall reaction, we have my reaction intermediate, the NO3. It's not included because it's used and then it's created and then we use it up. So this is my overall reaction. And earlier we just said that intermediates cannot be included in my rate law. Okay, so if I were to create a rate law, I know that it's my second elementary step that is going to determine my rate law because it's slow. So you would say something like this. So you would say that the rate of the reaction, I'm going to take the coefficients here. So we have NO3 and it's NO, right? And we don't include the product. So this would be your rate law just using that second step. But the issue is I don't want to put nitrogen trioxide here because this is an intermediate. So this can't go in there. So according to what we just wrote down, we're going to take out the intermediate by introducing it in terms of the things that made it up, and then we're going to just substitute that in. So if I were to take my second equation here and just rewrite it, I want to get rid of the NO3 right here, and I'm going to do that by just plugging in the NO and the O2 since that is what made up the NO3. So I'm going to just rewrite my equation. We have NO plus O2, and I'm substituting the NO3 right there, plus NO gives me 2 NO2. So this is my slow rate determining step where I substituted out the NO3 and then I added in the NO and the NO and the O2 because it makes the NO3. So that's where these guys come from. And then that's that and that is that. So everything else is the same. Now, if you were to rewrite this, we have 2 nitrogen monoxides here. So you get 2 NO plus O2 gives us 2 NO2. Okay. If we substitute that in, it actually ends up being our overall reaction itself, right? It just happens to be that way. It's not always going to work out that way. And from here, we could take this and turn it into a rate law. So we could say the rate is going to be nitrogen monoxide squared because of that coefficient of 2. And then we have the concentration of oxygen gas. And that's it. So this would give us our rate order for this overall reaction based on the slow rate determining step. And it is just by accident that my overall reaction ends up equaling out the rate law for this one over here.